All right, more counting today. So let's see, last time, what did we talk about? We talked about the basic principles of counting, and the pigeonhole principle. So today, we are going to do more of both of those things. So we left off with the pigeonhole principle last time, so we're going to start with more pigeonhole principle. And then we're going to go into more counting. And talk about permutations and combinations, which are two of the, more basic but a little bit higher level ideas for counting things. But first on the list is more pigeonhole. So let's recall what that says. The pigeonhole principle says n plus 1 pigeons are placed in n pigeonholes then some hole must have more than one pigeon. Great. And this is just because, well, actually, I don't think we said this very explicitly last time. So let's talk about why this is. I mean, kind of, it's a little bit obvious in this situation, but let's give it a little justification, because this is how we're going to generalize it. So because, if not, so if every pigeonhole has at most one pigeon, if not, then the total number of pigeons is less than or equal to, so we just add up all the number of pigeons in each hole. So n pigeonholes. We get n pigeons total. If there's at most one in each hole, there's at most n total. And this is, a contradiction. Because that's less than n plus 1, which is the number of pigeons that we said we had. So this idea, the pigeonhole principle, as we stated here, tells you that if you have one more pigeon than pigeonholes, then you're going to have 2 pigeons in some hole. But basically, this argument can be adapted to a much wider variety of situations. So here is one generalization, although there are more. And I think on the practice problems, I've given you a problem which will use a generalization that is not exactly what I'm about to say, but you can prove it in a very similar way to this, where you just consider what happens if you don't have this, and you add things up and they don't stack up. So let's actually say something. More generally, if we have n pigeons in k holes, so now instead of n plus 1 and n, I have just some big N and little k. So these can be any numbers. So if n pigeons are placed in k holes, then some hole must have at least n over k ceiling pigeons. So let's delve into this a little bit. First of all, if this sort of top side bracket notation is unfamiliar, this means ceiling which just means round up. So for example, n plus 1 over n, this is some number that is slightly bigger than 1. So for example, if so the claim is that this thing is equal to 2. And that's why, if we take this statement and do it in the case of n plus 1 and n, we get the same thing because it's telling us there's at least 2 pigeons in some hole. And just to be super precise what we mean by ceiling, for example, if n equals 10, then we get 11 over 10 ceiling, which is 1.1 ceiling. And round up means that we round this up to 2. So this is what, this is how we justify this statement. Or this is how we explain the statement. But what is the similar justification? Because, so if we have n pigeons in k-holes, we have to have at least this many pigeons in some pigeonhole. Because if not, so if we have strictly less than this many pigeons, let's count how many pigeons we have total. If not, total number of pigeons is at most, so we have k pigeonholes, so we'll multiply that by the number of pigeons in each pigeonhole, which is at most n over k ceiling minus 1. And this is strictly less than, so it is a fact about ceiling, which is to say rounding up, that n over k ceiling is less than n over k plus 1. As you can see in this example, this is less than 2.1, which is what we would have got by adding 1 to this. So basically the idea of this is just that whatever you round up by is going to be less than 1. If you were rounding up by 1, that meant you were already an integer to begin with, and there was no need to round at all. So this thing is smaller than this thing, so we can do that replacement and get this inequality. So this is strictly less than k times n over k plus 1 minus 1, which is k times n over k equals n. So actually, let me replace that slightly misleading thing and put it over here. And just, to say clearly what we've shown, the total number of pigeons is strictly less than n, is what we just showed. And of course, we can't have that if we are putting, if we're saying from the start that we're putting n pigeons in these holes. So this is a little bit of a long-winded discussion, just to say that if you have something besides n plus 1 and n, then you just need to take this ceiling and see what that gives you. So for example, last time we gave this example that if there's 13 people in a group, then 2 of them must share the same birth month. Now let's consider, what is our whole class? So there's about 40 people in the class. In the class of 40 people, there must be a group of at least 40 over 12 ceiling, So what is 40 over 12? It is 3.3 repeating. So the ceiling is 4. There must be a group of at least 4 people with the same birth month. So the difference is that if we were using the naive pigeonhole principle, or the first version, we would say we have more people than birth months, so there must be 2 people with the same birth month. The updated version allows us to actually say there must be 4 people with the same birth month. So it's sort of a better bound by doing this computation. Right. Very nice. So just like last time, I also want to give a little bit more sophisticated example of the pigeonhole principle, which we will use this slightly more generalized one, which is Ramsey theory. Which again is the thing about graphs, just like the example we gave last time. So Ramsey theory, just to give a quick spiel, Ramsey theory is about having guaranteed structure in sufficiently large systems. So what do we mean by this? Let's give an example. Oh, lots more space. Claim, if we take any graph with 6 vertices, and we color each edge red or blue, let's see, do I want to say that? I think I want to say this slightly differently. So let's bear with Sander for a second. Right. So for any graph with 6 vertices, let's not worry about coloring the edges. I was going to say color the edges, but instead I'm just going to say that for any 2 vertices, there might be an edge between them, or there might not, right? That was the thing that I was going to say in terms of coloring, but let's forget the coloring and just say that there might not be an edge. That's the thing that you can do in graphs. So what we could say is that for any graph with 6 vertices, there must be 3 vertices all connected, like all connected to each other, forming a triangle, or 3 vertices, none of which are connected to the others. So this is a slightly abstract statement if we're going to say it in terms of graphs. We can translate this to maybe a more familiar statement. So here's the people version. In any group of 6 people, so I'm taking an edge in this graph to mean that those 2 people are friends, and I'm taking no edge to mean that those 2 people are strangers. So in any group of 6 people, there must be 3 mutual friends or 3 mutual strangers. So maybe to illustrate this idea, let's take a counterexample. For 5 people, well, if we have 5 people, let me see if I can, how good of a pentagon I can draw. Is that a pentagon? Yes, it is. So if we say these people are all friends with each other, and those are all the friends we have, then as you can see clearly, there is no triangle, so there's no three mutual friends, and it's not quite as clear with leaving them out, so let me dot them in. There is also no triangle of dotted lines, which means that there are no three mutual strangers. So this is an example where you don't have this property. This is why it's not obvious. So the claim is that if you have 6 people, you always will have either 3 mutual friends or 3 mutual strangers. So let's prove this. So I'm gonna, I think I'm gonna prove it in this language of the people, but you can translate easily between the people and the vertices. So choose any person / vertex that we'll call A. Then there are 5 other people and each of these 5 people is either friends with A or strangers with A. So by the general pigeonhole principle, five over 2, so there are 2 options, right? They are friends or they are strangers. Those are the 2 pigeonholes. And the 5 people are the 5 pigeons. And this ceiling is equal to 3. Because 5 over 2 is 2.5. So there's 5 other people. And by the generalized pigeonhole principle, there must be at least 3 people in one of these 2 pigeonholes, which means A must have 3 mutual friends, must have 3 friends. So we don't yet know that they're mutual friends, but there must be at least 3 friends of A or 3 strangers. So let's there's either 3 friends or 3 strangers. Let's just say there's 3 friends. The argument for 3 strangers would be exactly the same, but just reversing the words friends and strangers. So we have our person A, and then we have 3 people B, C, and D, who are all friends with A. Let me draw this a little bit differently. I want C over here. Cool. So you have a diagram that looks like this so far. So if any of B, C, and D are friends, then that makes a triangle with A. So for example, if B and C are friends, we have that edge, then you can see that this is a triangle, which is to say that A, B, and C are 3 mutual friends. Or similarly, if B and D are friends, you get this triangle, and so on. So the only other possibility is if none of B, C, and D are friends, so if it stands as we sort of drawn it now, let me dot in these lines that don't exist, then you can look at what we've just drawn. B, C, D forms 3 mutual strangers. We have this triangle of dotted lines that we've drawn here. So just as we claimed, we must have either 3 mutual friends in this case, or 3 mutual strangers in this case. So that proves the claim. So this is a nice little example of using the more general pigeonhole principle. And it's also a very nice example of some curious mathematics. So let me say a couple more words about this, just for just for your general education. The Ramsey number RMM is the smallest number of people required to do this with M friends or M strangers. So in any group of people at least this big, you can guarantee at least M mutual friends or M mutual strangers. So you can see we have proved that in a group of 6 people, you must have 3 mutual friends or 3 mutual strangers. And we gave an example to show that in a group of 5 people, this is not necessarily the case. So that constitutes a proof. We had proven that R33, so the minimum number to guarantee 3 mutual friends or 3 mutual strangers, is 6. It is known that R44 is 18. But one of the really appealing things about Ramsey theory, about Ramsey numbers, is that it's a striking example of numbers that are quite small, but still very mysterious. So R33 is 6, R44 is 18, but R55, we don't know what the value is. We only know that it's between 43 and 48. So somehow, we know that it's a very small number. We know that it lies in this very small range, but it's totally an open question what the exact value is. It is really not easy to nail down. And this makes some kind of sense if you think about it, because there's a little bit of, 43 is a fairly small number, but the number of graphs with 43 edges, or with 43 vertices, rather, the number of graphs with 43 vertices is not small. In fact, maybe that's a good exercise to try and figure out that number, since we're talking about counting. But yeah, quite a nice example of small numbers that have still, for the moment, escaped our knowledge.